All right, I'm going to talk about 8.7 Taylor polynomials and approximations. This is actually the second part of this section. We talked about the other part in class. So this is actually what we came up in class. We talked about a Taylor polynomial centered at x equals c, so that's what we would have here. And f of x is approximated by this finite polynomial, n being really anything. It could be 1. It could be 100. One of the things we talked about yesterday, or when we talked about this earlier, was that the higher the degree, the better this approximation becomes. And then another thing that we talked about, even though we're not really going to get into that here today, is that the closer we are to the center, the better approximation we will have regardless of the number of degrees. Okay, so that's something we always want to talk about or think about when we're talking about accuracy, those two parameters. Higher degree, better approximation; closer to the center, better approximation. Yeah, okay. Now what we're going to get to today is, once we do a Taylor polynomial and we do an approximation, how do we know how accurate that approximation is? So we're getting into a conversation about error, okay? So one thing that we have to understand is this. So if we go with a finite polynomial, that's an approximation. However, for a certain interval, and you know, some of the ins and outs here are things we're going to be talking about all, you know, for the rest of this chapter. But on a certain interval, this function is actually going to equal to this thing if we continue on. So here's our polynomial, but let's say, you know, we add to it and we keep going. We go f to the n plus 1 degree. So that would be the next degree derivative, etc. And if we just kept going, you know, so essentially this becomes an infinite thing. So, you know, we could go, and I'm not just kind of trying to make you visualize this thing. If we just kept going here, and on and on and on. So this would now be an infinite thing. We go from an approximation to equals. So really what we want to figure out is what the part we chopped off is. So if this is equal to, if we ended a certain polynomial, then what that means is our error, and by the way, in this class when we talk about error, we talked about this earlier, we're always talking about the absolute value of the difference between the function and the approximation. We're not doing relative error or anything like that. Okay, so what we realize here is that this is actually equal to the remainder, the part that we didn't use here. So in other words, we call this remainder term. This remainder term is going to end up being all of this stuff. Okay, so the remainder is an infinite series in its own right. So this remainder term right here. So in other words, this would equal the absolute value, and then the part that we didn't use. And once again, this is on a certain interval of convergence, which is a big discussion moving forward. Okay, so that's the part we didn't use. Now, this isn't all that helpful, because if our error is an infinite series, how does that help us? Well, what we have is what is called Taylor's theorem. Our book refers to this as 8.7. And what Taylor's theorem says is that, this is 8.19, theorem 8.19 in your book. So this is what's referred to as Taylor's theorem. What Taylor's theorem says is there exists a z, all right, that's somewhere between our center and x being where we approximate. Now, our x could be on either side of our center, so it just depends on what the orientation of x is. So we could have it where the value's on the right of the center, so that means z would be on that side, or it could be that we're approximating on the left of our center, and our z would be in there. So Taylor's theorem said there exists a z such that, all right, and this remainder term. Okay. Let's get rid of the absolute value. We're not there yet because we're not talking about error yet. Is equal to one term with that z plugged in over m plus 1 factorial x minus c to the m plus 1. So what Taylor's theorem tells me is that it's not the same value as x, it's some z that we can boil this down to one term. One term. So we can get a hold of this remainder term in just one term, which is very, very powerful because now that allows us to get this. So what that means is our error is going to equal the absolute value, because this could be positive or negative, of this one term. Now, if you look at the verbiage here, this sounds very similar to a theorem we did last year, the mean value theorem. And if you remember the mean value theorem said there was a c that existed such that blah, blah, blah. I'm not going to get the ins and outs of that. And we spent some time finding that c exists, sort of, coming up with the idea that this actually holds. But in general, if you remember, we weren't so interested in actually finding the c. It was just knowing the c exists. This is going to be very similar to that we're not going to spend a lot of time necessarily finding the z, because a lot of times, in order to find that z, we'd have to know the exact error. The point is the z exists, which will allow us to sort of get a feel for the worst case scenario for the error, okay? And that's what's going to be important, and that's what I'm going to show you here. Okay, so here I've written out Taylor's theorem, and once again, this is what we focus on. We know that this is actually equal to an infinite series. There's a z that exists that equals to that part that we didn't use. So if we end at 5, okay, like if we do a polynomial degree 5 to approximate f, okay, the error will be equal to the remainder, 6, 7, 8, etc., all the way to infinity. And what Taylor's theorem tells me is there's a z exists where that whole remainder is equal to one term, the next term. So if I did a polynomial of degree 5, this would just be one term of degree 6. And the fact of the matter is, or what's important is that this z exists, not so much that we find the z or the exact error. Okay, by the way, another term for this, which they use on the AP test, is this is what's called the Lagrange form of the error. They'll say the maximum. Generally what we're going to look at is taking this Lagrange term and maxing it out, okay? And that's really the focus here. And keep in mind that this is going to equal the error, and that's what's powerful about it. So it's going to be the absolute value of this Lagrange error. And let me show you how we're going to do this. All right, so let's start off by doing a polynomial. So let's say we did the polynomial. I'm going to try to get this all in here. So let's say we do a polynomial f of x equals 1 over x. And let's say we're going to approximate that using our third degree polynomial centered at 1. Okay, so we're going to center that at 1. All right, so we'll start off by doing that. So understand what we're going to have here is we're going to say f of x is actually equal to, so we're approximating using this, is equal to this polynomial, degree 3, plus the remainder, which we want to get a hold of this because this is going to give us some feeling for the error. Okay, so we're going to start off like we did before. We're going to have f of x equals 1 over x. So we'll call that x to the negative first. Okay, f prime of x, we're going to take the derivative of that, so that'll be negative x to the negative second. Double derivative comes down, that'll be 2x to the negative third. Okay, the third derivative, so this is going to be the last derivative I need for my polynomial, so that'll be negative 6 x to the negative fourth, okay? And then we're actually going to need, so wherever you end the polynomial, because we use a next derivative, go one past that. Okay, so we're going to take the next derivative, so that would be positive 24x to the negative fifth. Okay, so now, as we did before, we're going to enter our center, so our center here is 1. You could change these exponents to positive, but realize since we're just plugging in 1, all of those, so for instance, 1 to the negative second, 1 to the negative third, 1 to the negative fourth, that's all just going to be 1. Okay, so what we're going to get here at our center is 1, negative 1, 2, negative 6. And the next thing we're going to do is divide by the factorial. So if we divide by 0 factorial, that's 1. If we divide by 1 factorial, that's still negative 1. If we divide by 2 factorial, that's 1. If we divide by 3 factorial is 6. We get negative 1. So we see this nice pattern here. So my p sub 3 of x is equal to 1 minus 1 x minus, oops, our center is 1. So x minus 1 plus 1 x minus 1 squared minus x minus 1 to the third. Okay, so now what we're going to do is we're going to approximate this. We're going to approximate f to 1.2. Now I want to start with this one because we can actually know what exactly this is. We're going to be able to find the exact error so we can see how accurate this is going to be. We're not always going to have that. If we always knew the error, then you know why would we need to do all this? We're not always going to know the error. All right, so anyways, 1.2, so that's going to give me p sub 3 of 1.2. And let me fix this. This is an approximation here. Okay, so what I'm going to get is 1 minus 0.2 plus 0.2 squared minus 0.2 to the third. And what I get there is 0.832. Okay, hopefully I'm not cramming this in too much. All right, so now, how accurate is that? All right, so what we're going to do is we're going to use this Lagrange form of the remainder to get a hold of our actual error, okay? So what Lagrange tells me is there's a z, so we know that there's a z that's somewhere between our center, which in this case is 1, and our approximation, which is 1.2, okay? And such that our remainder, or our error, is equal to the absolute value of the next derivative. So our next derivative here, which I'm going to call 24 over z to the fifth, okay, so I'm moving that to the denominator. We're dividing it by the next factorial, so that's just going to end up in the denominator, so that would be times 4 factorial in the denominator. And then x, not x, because we know what the approximation is. The approximation is 1.2 minus 1 to the fourth. So I know a z exists such that this is actually equal to the error. This is our Lagrange remainder, okay? And remember, the part we're not using here is actually going to be the difference between the actual answer and our approximation. Okay, now here's the thing. I don't need to know what z is. I know z lives somewhere between 1 to 1.2. What I'm interested in is maximizing this thing. So what I'm going to do is I'm going to choose the z on that interval that will maximize this thing. Now realize, since z is in the denominator, as this thing increases, this whole term actually gets smaller, right? Now if z was in the numerator, it would be reversed. So what that means is I'm going to choose z, so I'm going to choose z equals 1 to maximize this term, okay? And I'll tell you, it's usually pretty basic, and we'll get into some other possibilities, but usually you're going to choose the left-hand endpoint. If, in this case, if it's going to decrease, we choose the right-hand endpoint. for instance, if this was in the numerator, if it increases, okay? So now I know that this is going to be less than, choose z to be 1, I'm going to know this is going to be less than 24 over 4 factorial. 4 factorial is 24, 0.2 to the 4th. So 0.2 to the 4th is equal to 0.0016. Now what we refer to this as the error bound. This is the most the error can be. We know the error is less than this term. Okay, so now let's just take a look at this. So this is, we're saying the error has to be less than this. Well, let's just experiment to see that this works. Notice we didn't find that z here. So we know actual, because f is just 1 over x, so that's equal to 1.2 minus our p sub 3 of 1.2. This is what the error actually is. Okay, so go ahead and grab your calculator and calculate this. This isn't rounded, by the way, so we can just use this. And what we end up getting is the actual error is 0.0013 repeating. So this is the actual error. This is what the error is equal to. This is our error bound. So you can see that this is very good because our error is slightly less than what we're saying is the max. If that was the other way around, we'd have a problem. This is what's generally important to us. If you think about what we're doing here, we're taking a function, we're approximating with this polynomial here, and what we're saying is the worst case scenario is that the error is going to be 0.0016. Actually, we know the error is less than that. Okay, so that is Taylor's theorem. I'm going to do one more example here, so we can refer to this as example 1 that has a slightly different feel to it. Okay, so example 2, we are going to do the Taylor polynomial for cosine x, degree 4, centered at 0. So once again, our textbook refers to those as Maclaurin polynomials. Okay, and so first of all, let's just go ahead and get that calculation. So they actually provided the actual polynomial, but we do have to look at how that's built a bit because that's going to inform the whole process here. So anyways, so we're doing cosine of 0.1, okay, which is approximately our degree 4 polynomial of 0.1. So that's going to equal 1 minus 1/2 0.1 squared plus 1 over 24.1 to the 4th. So that gives us, by the way, you want to do a few decimals here because this error is going to be so small to actually see what's happening. We have to go kind of small here. So this will be 0.99500416667. Okay. So I did the whole decimal that it showed there. Okay, so let's first kind of confirm that this is what the polynomial is. So first of all, we're centered at 0. We would start with cosine x. Okay, our next derivative would negative sine x. Okay, that explains why we're getting a negative here. Well, I guess with the double derivative. Then we get negative. Negative cosine x. And our triple derivative is going to be positive sine x. Fourth derivative is going to equal cosine x. And so if you look at what's happening here, if we plug x equals 0 into this, we get 1, that's 0, that's negative 1, 0, and 1. So that gives us that alternating, and then we divide by the factorials. Now, because we're doing this Taylor's theorem, you always have to go to the next derivative. So let's go ahead and find that. Our fifth derivative is going to equal negative sine x. Okay, so here's our approximation. So using Taylor's theorem, we know that there's a z that is somewhere between our center. So the center is 0, and we're approximating 0.1 such that the error is equal to the absolute value of the next derivative, so that's a negative sine of z, over 5 factorial, and then 0.1 minus 0 to the 5th. Okay, so we know that exists. Now, here's the thing. When it comes to sine, so just like we did last time, we're going to maximize this term. Well, the way it works when we have sine or cosine, and realize we're taking the absolute value, if you take the absolute value of sine x or cosine x, we always know that's less than or equal to 1. So we don't have to focus on finding the z. We know that this term, the absolute value, would be less than 1. So I'm just going to replace this with 1. Same thing would be if I'm doing cosine. So what I end up getting here is this is going to be less than, okay, and this will be 1 over 5 factorial, 0.1 to the 5th. Okay, so now I'm going to calculate this. This is our, keep in mind, this is our maximum error. Error cannot be higher than this. Once again, some terminology, this is what's called the Lagrange remainder term. So this is going to equal, and actually it's very, very small, and that's why I went so far out with this. So 8.3 repeating times 10 to the negative 8. So keep in mind what that means is we have 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then 8, and then the 3's go on and on and on. So the worst case scenario for our error is right here. Our error has to be less than that. So that's a pretty good approximation. Now, so this is our approximation. This is the maximum error bound. We can also, and sometimes they have you do this, sometimes they don't. Don't get confused here. But if I want to get an idea for what the actual value is, I can do f of, or I guess we can call it f. So cosine of 0.1 is going to be between 0.99500, etc., plus that. So that would give us 0.99500,425. Same thing for the back end of this. I can subtract. I can take this and subtract this, and I get 0.99500,408. And cosine has to be somewhere in between those two things. I'm just adding and subtracting the error on each side to my approximation. Now, since we have use of our calculator, and let's go ahead and calculate this and just see how well we did. So cosine of 0.1, okay, 0.9950041. So that definitely works. It is definitely between these two things. That is Taylor's theorem. I will tell you that, this is one that takes a while to digest, so we're going to work through some problems. And if you're sort of having a hard time wrapping your brain around this conceptually, we don't have to worry about that today. That this is something that hopefully will become more comfortable to us as we go on. All right, so that is all of 8.7.